Hello everyone, welcome. This is class ECE317 digital signal processing. We already learned something about systems, right? And we know how to find the output if input is given, how to find the output. And today we will study, do some like a case study, all right? Yeah. Okay, this is a ECE317. This is the fourth week, the Friday's class. Right? Okay, we say this is a kind of a case study. We consider a system. Consider a system which is a y of n minus 1/2 y of n minus 1 equal to x of n minus another number like a 2/3 or x of n minus 1. Okay, so this is a system, right? We have a system. This is a LTI system. Then we can study several things. The first one we consider how to find, the impulse response. How to find the impulse response. So far, actually, we have several ways. The first way is solve the equation. First way, solve the equation. H of n minus, the h is the impulse response, right? H impulse response minus h of n minus 1 equal to, this side will be dirt of n minus 2/3 dirt of n minus 1. So we can write it as h of n equal to dirt of n minus 2/3 dirt of n minus 1 plus 1/2 h of n minus 1. Okay. So we can use this formula. We can use this formula to find what is h. What is h? We plug in different value of n, then we can know different n, like different value of h at n. And like h of -1 will equal to dirt of -1 minus 2/3 dirt of, here's a -1 minus 1 is -2 plus 1/2 h of -1 minus 1 is -2, right? We can have this. And h of 0 will equal to dirt of 0 minus 2/3 dirt of -1, not n 0, right? And plus 1/2 h of -1. And h1, there will be dirt of 0 minus 2/3 dirt h of 1. Now here's the dirt of n is 1 now. So 1 minus 1 is 0 plus 1/2 h of n minus 1. n is 1, 0. So we can keep working like this. Then we can have all the values of h. Right? This is a way we can realize in computer. Let me go to MATLAB. Can I have both? MATLAB. All right. Okay, so the things, I use a file. Okay, create a file. The thing like you want to find output, right? Okay, So here's this formula, this one. Okay. We need to do this time again for different n. So we have a dirt. We have input x. Now x is just 1. Okay, I give capital N. Capital N for the like a 50, which is the maximal time for a signal. Right. Here's the time integers. So we just suppose the we only calculate until n equal to 50. Then I need a time n. I need a dirt. Dirt is x. Right? X is dirt. So it will be first element is 1, then zeros. All the rest are zeros. Right? So zeros. This is 1 row and n minus 1 columns. And 1 row and n minus 1 element in this row. So this is the x. This is x. So we have I just type. Okay, this is x. Then what will be that edge? You need a edge will be okay. We need a loop. So I suppose firstly I give edge. I give the size of edge. Suppose edge is just x times 0. All right, x times 0. Yeah, you can also use other way to find it, to give it. That means edge is a vector. The size is same with x, and all the values are 0. And now we calculate the edge for I run from 1 to n. Right, totally we have n element, 1 until n. I need edge of I equal to, okay, I use this formula, right? It is delta n minus s. It is x of I. No, I is the n. Yeah, I can use. Oh, I already use n. xi minus 2/3 times x of I minus 1 plus 1/2 0.5, right? Times okay, I need edge. Edge is I minus 1. Yeah. So basically we need this. By this one we can have edge, right? But we have some problem, because when I is 1, here you need x of 0 and edge of 0. You see, when I is 1, you need edge 0 and x of 0. But we do not have x of 0 and edge of 0. As a vector, the first element, the first index must be 1 in MATLAB. So here we start I from 2. And when I is 1, I need to write it especially. So edge of 1, I need to write it directly. Edge of 1 is here, right? F1 is here. This one, you see. Edge of 1 is third of 1. Oh no, edge of 1, actually this is edge of 0. The first element of edge, according to time, is 0. Time is 0. And then there will be dirt at time 0, that is 1. Right? And minus 2/3 of dirt at -1, this is 0. And edge at -1, we also think it is 0. You know, because that is the response before you give input, right? The output at time -1, no input, because delta, we have first delta value is 1. Before that, delta are zeros, so we think h is also zeros. Okay, so h1 it is just 1. H1 it is just 1, just delta of 0. Okay, I can put the n here. Put the n for the time. N run from 0 to n minus 1. This is for time. Okay, So by this way we can have all the edge. And then you want to see how it looks like, you can use stem and the edge, right? You can see what it is. Okay, let's run it. I need to put it somewhere. Okay, and go to desktop 317, and I have code, MATLAB code. So today this is a lecture, the fourth week, Fridays. Okay, it's like this. Okay, then I add this direction to the MATLAB path. Okay, I run it. Okay, then we have result looks like this. Oh, the first one is negative. Oh, so here first one is 1. First one is here 1. Then go to some negative value, then increase until like almost 0. Alright, so you can have edge by this way. But this is a kind of a computer way, a calculation way. You will have a list of values, not a formula, And actually in MATLAB they have a building function. I say this is a this edge, right? I use edge 2, which is a impulse of, I need to define the system. So the system, my system is, I use SS. Okay, SS. What is system? Actually, let me close it. The system is here. System here, right? System is here. So we can define system by the building function field. Yeah, in most cases we call system is a field. Then I need to put the coefficients. Input coefficient in the front, there will be 1 and 2/3, negative 2/3. And output coefficient is here is 1 and negative 1/2. Right. So this is the SS, the system SS. And then I let H1. I use the building function impulse of SS, just like this. Oh, I need how many days? I have 50 days, right? So I use 50 days. I put 50 here. Then I can also have 50 days. H1, and I can also, now I use a plot. Okay, plot and plot, just plot H1. Now I compare these two. I put the hold on. Then I can have both picture together. And before that, I need a close, or if I have some window open. Okay. Now run it. I have two together. Oh, I have one shifted because okay, I need an N. The stem is, I use N here, so it start from 0. So I remove it. Then there will be the same. Or I put N here. If I put N here and N here, they were same, right? Alright, you see the graph. The plot gave us a curve. So this curve, this blue line, this is curve. Use a plot, and those circles, they are coming from the stem, right? Stem is a bar from the x-axis go to that circle, right? Yeah. So actually they are same thing. You see, totally same. So you can also use the building function. Actually, the building function same thing. If you look inside, you should find something similar with this, But this is a MATLAB. In MATLAB, so this kind of summation you can write in a shorter way. I put it here. You can in a shorter way. This one, you can write in this h equal to a times b, where a equal to delta of n minus 1, delta of that is h of n minus 1. It's a vector, row vector, and the b is a coefficient as a column, is 1, negative 2/3, and positive 1/2. So a times b, that you see a row vector times a column vector, right? Remember, this is in linear algebra. A vector, row vector times a column vector. The result will be element times element, element times element, then do a summation. So element times element, do summation, so you get h. So in MATLAB you can write in this way. We will have a lab experiment. Which one? I forget. Yeah, lab 2, 3, or 4. Yeah, you need to try to realize a system in a way like this. Not just for the impulse response. Here, delta input is delta, right? In generally, you can use any kind of input. Any kind of input, find any kind of input, find any kind of output. Yeah. Okay, so this is for the input for the impulse response. Okay. Then we also know the frequency response, right? So frequency response. Second thing is I have 2. I said 1. Yeah, then 1 is here. I already have 1 here. Frequency response. Frequency response. So what is the frequency response? Now we already have impulse response, right? We also have the equation. So here we have 2 ways. The first way, I say this is h of e to the j omega or equal to, you can write it directly from the equation. So this time is a numerator is coming from the input. There will be 1 minus 2/3 e to the negative j omega. Right? The first one is x itself, nothing changed, so here's 1. Second, we have a coefficient negative 2/3. Copy this coefficient and shifted of x, so you times e to the negative j omega. One shift, then one of these. If you have shifted by 2, then here you need times 2 here. Right. Okay, similar for denominators, they are coming from the output. So this is 1 minus 1/2 e to the negative j omega. So this is a frequency response. And the second way, we can have the frequency response. We have h here, right? We already have h. So h of e to the j omega equal to dtft, discrete time Fourier transform of h of n. So we have 2 ways to get it. However, so far right now, right, for this example, I just give this one, and I have the number. I calculated this way. I calculate some numbers. I have those numbers, right? The numbers I show here as a graph, and also I can see they are h, right? They are just h, so I can see the numbers. I list number here. You can see all the numbers, but I do not have a formula, right? I do not have formula. To find the formula of h, you need to observe the data and try to find the formula. That is something, depends. Some case you can like this one, I think it will be easy to find that edge. But sometimes this is not so good, so easy, not so easy. If the for this one, can we find it? Or just according to the number, let me see. I copy some number to see. Can we find okay, the number h of n will be 1, the negative 0.1667, the negative 0.0833, the negative 0.0417, and so on. Can we find the table or find the formula from these numbers? Not so easy. Actually, so far, like me, I look at this number, I have no idea what will be a formula for them. Get it? So this way is somehow not so easy, right? You calculate this h, but no formula, and then you perform DTFT. You still do not have formula. You can just write in this way. It is h of n, then e to the negative j omega k, hk. K run from negative to positive infinity. You only know this definition. You can plug in the value in and get it. There will be a lot, right? You plug in this here, then you get it. It's a kind of a numerical calculation. So if you want to find the formula, you need this one for formula. Actually, you already have the formula. Okay? This is the formula. This is the formula. And then 1 give h of n in formula. H of n is the inverse DTFT of h. It's positive, which is a inverse DTFT. I just write f. Okay, Fourier transform, inverse Fourier transform of inverted Fourier transform of this one. It is 1 over 1 minus half e to the negative j omega minus 2/3 e to the negative j omega times 1 over 1 minus half e to the negative j omega, right? Then the first part gives us 1/2 to the n u of n. Right? You check the table, you can have it. And second part is minus 2/3. This part you have 1/2 to the n and the u of n, right? But you multiply, you times this one. This one times you have this one. This one go to time domain. You need to shift by 1. So minus 1 and minus 1. Okay, so you have h of n in formula. You have h of n in formula. Alright. Yeah. We can try this formula whether it is good. N equal to 0. I have h of 0 equal to 1, right? N 0, this is 1. This is also 1. Minus 2/3 times n is 1. N 0. N 0, this gives us 0, right? N 0. 0 minus 1 is negative 1. U of negative 1 is 0. So just times 0 is 1. And n equal to 1. H of 1 equal to n equal to 1, this is 1/2, right? This is 1. And minus 2/3 times n is 1. So this is 1/2 power to 0. This is 1. The power 0, right? And when n is 1, this is u of 0 is also 1. So is 1/2 minus 2/3, 7. Okay, so it's negative 0.1667, right? Okay. You compare the this. It is here. I'll see. Compare it here. first two letters, first two numbers, right? We get the first two numbers. Alright, 1 and negative 0.1667. Yeah, for two numbers. If you want to try, you can try more. And if you want, you can also put this in computer. You will see they are totally same. Totally same. Alright, so this is for frequency response. But here actually give us a way to find the impulse response. We try to find the frequency response firstly, then go back to the impulse response. When we learn it, remember, do you remember we have class by class, right? We learn step by step. We learn what is h of n firstly, and then later we know, okay, what is a frequency response. But now you have both, right? You know both. So when you want to calculate, use this firstly. You find this firstly. Find the impulse response before, after you find the frequency response. You do this firstly. You do this firstly. Yeah. You do this firstly, then you invert. You use the inverse Fourier transform. You can have h of n in a formula way. In a formula way. All right. Okay. This is the frequency response. Now we suppose. Now we consider the input and output. Input and output. Input to output. Input to output. Input to output. Of course, when we have the equation, we can find the output by this way. Now I just change here. I change x, like I use the same x notation. I use x equal to whatever, like a random value. Random value. The size is 1 and capital N. I use this as x, and I do not use these first x. Okay, first x. This is impulse, and this is impulse. This is impulse. Now I change different x, a random value of x. Then here it won't be h. I use y. All right. I change here. Use y. I change here. Use y. This is y. Y is x minus x plus another. Here should be y. Okay. Then I can have y. Then I can see how y looks like. And hold on, I can try use system way to find this y. This is y1, and plot y1. Here's but okay, I cannot use impulse response. I use another one. I use a y1 is a LSIM. This is a function you give the system is here, and the input is x. Okay, I think it will be fine. Yeah, so we have this one. We use this one. By this one, we can have another y1. Then let's compare both. What will happen? Save and run. Oh, it is one. Yeah, you see, this is the curve. I can use different color. Let me. I use a plot y1. I use a red color. All right. That means a red color. Okay. All right. It's here. Yeah. The red color. Why here is different? Only here is different, but all the rest are good. Oh, first few numbers are different, but the rest part are good. let me see, we have something wrong. So x is randomly, and I use these to do the calculation, and here I use a field s and x. Oh, I forgot this one. Now this should be not 1, right? y1. This is y1. y1, I still need to use this formula. Because firstly I use this here is for dirt, right? For dirt. Input is dirt. But now the input is not dirt. Input is not dirt. Input is, so input is what? It is x1, the I is 1, minus 2/3 of xi minus 1. Okay, this part should be 0. This is 0. Oh, just x1. That's replaced by x1. That'll be fine. It's just same formula, We use the same formula. Same formula. So here should be same formula, but we know x of I minus 1. I minus 1. That is I0. I should be 1. So this should be x of 0. Go back to the negative side, should be 0. This is also 0. Okay, so this time should be good. Let me see. Alright, totally same, right? You see? The blue circles is coming from stem. This is calculated by directly from the equation, and the red curve is obtained from the building function of MATLAB. So they are same thing. Here actually, you know what? Now you are study. You use MATLAB. You can write all the code using MATLAB. However, when you go to the real job, when you want to do some, you want to create some real things, you cannot use MATLAB, because MATLAB it's run slow. You can write shorter code in MATLAB, because MATLAB provides a lot of building functions. So you can write the code in a very short code. You do not need you do not need pay a lot of time to write code, right? Shorter code. Then long running time. Yeah, shorter code but longer running time. So this is MATLAB. Then when you really want to build some system, you prefer use C or Java or like Python something. You want to use MATLAB in the real application. So you should understand what will be the function behind those building functions. So here, like this part, actually it is same way this one, same thing. But in MATLAB you just use this one line, you can realize it. And if you want to write code by yourself, you need to write so many lines, right? So many lines. So in MATLAB you can save the time to write code, but you should understand what will be the real thing. Okay, so this is the output. But this output is also kind of things you do not have formula. Do not have formula. Of course, in this case, I gave x. This is a random signal, right? Randomly. Every time it will be different. Let me run it again. You see, it's different, right? Different ways previous one, right? Yeah. Are they same? Different, right? You remember? Like look at it again. Let me run again. You can see whether they are same. I run it again. See, they're different, right? Obviously different. So the signal is randomly. X is randomly, and then what will be the output? The output will change according to the input. So every time is different. Now we consider. Suppose we have input is with a formula. Okay. Then I need okay. I put n in the front. And after n, I use x is like a 2 of cosine. I use a frequency which is pi over 30. Okay, this is low frequency, right? Times n, and plus 3 of sine. I use a frequency is a pi over like 3. So this frequency is not so lower. It's kind of middle, right? Times n. And another one like minus 2, 3. I use 2 again. I use 2.5. This is amplitude times another. I use cosine again. And frequency, I use a high frequency. I use like 7 over 8 pi as frequency. Alright, so this signal is combined of 3 parts. Each part 3 sinusoid, right? 2 cosines, 1 sines. And the frequency is 1 over 30, pi over 30, pi over 3, and 7 pi over 8. Here, okay, so x I write here. X is x of n is 2 cosine pi over 30n plus 3 sine pi over 3n and minus 2.5 cosine of 7 over 8 pi n. Okay, this is high frequency, right? And this is low frequency. And for discrete time signal, these are the highest frequency. Well, this is quite different with the continuous times case, because when the frequency higher than pi, you minus 2 pi, like pi plus, for example, whatever, like some dirt, small value, then minus 2 pi you will get negative pi plus dirt. You see, here's pi plus dirt. If a frequency is here, there will be negative pi plus dirt. So this one, they are same frequency. And we use the value between negative pi to positive pi as the main interval of the frequency, just negative pi to pi. Over pi, it will go back to here. And another side is the same. If frequency is here, you plus pi, you will go to here. So any frequency you plus or minus some 2 pi's, that frequency will finally go to inside this interval negative to positive pi. 0, of course, is the low frequency, right? Then going up to pi, that is highest. Then it will go back. Right? If you go outside, it will go back. So the high frequency is just the positive negative pi. And also cosine pi n is what? 1, negative 1, 1, negative 1, right? Here's n equal to 0. So you see, the value of this signal will change from 1, go back to negative 1, then positive 1, then negative 1. Change rapidly. Well, what is frequency? That gives us the kind of measurement about how fast, how rapidly the signal oscillate, right, up and down. So this is most rapidly. Yeah, most fast change on the value. Positive, negative, positive, negative. Any other signals, if like from positive to positive, then negative, That is the frequency, of course, is lower than this, right? Yeah, this one just go back, positive, negative, positive, negative. So this is the fast one. No signal can change even faster than this for discrete time signal. All right. So here I use these three frequencies. Then what will be the output? What will be output? If you just look at it in this way, we can have a look. Okay, so this is the output. This is the output. This is output. Nothing special. You just look at here. Seems like a lot of data here. You cannot find the regulation. However, we can go to the frequency domain. We can have more information. We can have more information in frequency domain. The input, here in frequency domain, the input, we have three terms, right? We have three terms. Yeah, we have three terms. So it will be looks like you will have three parts. Three parts. The lower one will be pi over 30. The higher one will be the frequency. Here's the frequency. Will be 7 pi over 8, and this one should be pi over 3. Should be looks like this. From negative pi to pi. Or if you want to use from 0 to 2 pi, similar. You have 3 here, another 3 here. Something like this. Yeah, we can have a look. This is the input x. This is will be x of e to the j omega, right? X of e to the j omega. And what is this one? This is a Fourier transform of x of n. All right. We have the. You can check the table. You can check the table to find them. You can also use MATLAB to have a to look at it. Use a graph. You see. I use a figure 2. I have x, right? So I have capital X. X is a function of omega equal to. I use fx. Okay, fx. Fourier transform of x. Just FFT of x. So this is a building function of MATLAB. And then I figure 2. I plot. I use a absolute value because it's a complex number. So I see the complex absolute value. All right. Oh, it's not good. So I think I need a. Oh, I put the x. Sorry, fx. Yeah, I put the fx. Yeah, and now it's good. You see, this one. Actually, in the ff function, this fft function, it will be run from 0 to 2 pi. It should be 0 to 2 pi. And yeah, I put w depending on the size of x. The x, we have size 50, right? I use 50 numbers. Use n numbers. So here I also use n numbers. There will be 0 to n minus 1. This gives us n numbers. And the times 2 times pi over n over n. Okay, this is w, and I put w here. Plot. I use w here. All right. Okay, so from 0 to 2 pi, there's 6 dot something, and we have 1, 2, 3, 4, 5, 6 peaks. 6 peaks. Will be this one. Will be this one. Yeah, from 0 to 2 pi, we have 6 peaks. Each peak, they according to that frequency. So this one here should be pi over 30, and then this peak is related in pi over 3 around 1, right? Pi over 3 almost equal to 1, and this one is 7 over 8 pi, 7 pi over 8, 7 pi over 8 is close to pi. Pi is 3 dot something. This is close to pi, right? So we have these three. This is x. This is x. And what is y? We already have y, right? We another one is y. So we do the similar thing. This is figure 2. Again, figure 3. And just copy this. Figure 3. Figure 3. Now is use y as to do the Fourier transform. And same w, I want Fourier transform of y. Okay. Alright. I have two things. So figure 2 is x input. Figure 3 is output. You see, we still have three parts. That means the output side will keep the frequency of the input. The input we have 3 frequency. The output also have 3 frequency. Right? But the amplitude is changing. In the input side, the frequency. This one is the peak value are related with the amplitude of each component, each frequency. This output side, see the lower frequency obviously reduced, right? The other two is similar, but the low frequency is reduced. Why we can have this? You can also check the frequency of H, right? We know what is capital H. That is frequency response. You can also have the frequency response. Frequency response. Do I have frequency response? Okay, I can calculate. That is a figure. I can give figure 4. This is frequency response. That is a H. H will equal to. I think I write it here somewhere, right? It's here. This one. Now I give a graph of it. Let's give a graph of it. Oh, time is almost done. Almost done. This is a something over another one. Numerator is 1 minus 2 over 3 times exponential power of negative j times omega times omega. Right? This is the numerator, and the denominator is 1 minus 1/2 times exponential power of negative j times omega. Am I good? I think it's good. Then let's plot. Okay, I still use omega and absolute value of this h. What it is? Oh, sorry. Oh, not x. I put the x. It should be w. Sorry. Okay, so this is the frequency response. This is a capital H. I want to see both, all of them. This is figure 3 is output. This is the input. Can I put them together? This is the input, and this is output. So we know input in frequency domain should be input times the frequency response. You can have the output, right? This is the frequency response. You see, for the frequency in the middle, around the pi, that is high frequency. For high frequency part, the system has magnitude is 1, close to 1. So for the output side, for this high frequency part, the change is just a tiny change, a little bit change, right? You see these 4 peaks actually according to 2 frequencies. The change is just a little bit, but for low frequency is this part. The value here is small. That means we times this small number on this peak, we get this peak. So here should be 50 around, right? After times this value should be like a 0.6 or something. Here's 50 times 0.60, you get 30 something, right? This is around 30 something. Yeah. So things like that. So input value, input in the frequency domain times the frequency response, you get the frequency domain of the output. And if you perform inverse for the transform of these, you can have the time domain output. All right. Okay. That's all for today. Actually, I just want to show you what really happened for a system, for a signal using input and output. Right? Okay. That's all for today, and this is Friday, so see you next Monday. All right. See you next Monday. Bye bye. Have a good weekend.